Now that we understand charge sensors, quantum dots, and multiple quantum dots, we can focus on the physical implementation of quantum information. Quantum computation with quantum dots is explored in many different ways. A first attempt may be to directly use the charge of an electron as the qubit state. In a double quantum dot, the electron may be tuned to be in the left, the right, or in the superposition of the two quantum dots. The ground state energy is determined by the detuning energy, the energy difference between the energy level on the left and the right quantum dot. Thus, by controlling the detuning, the state can be manipulated. This two-level system then provides a physical implementation of a qubit, and we call it a charged qubit. Interactions between qubits may be obtained via the capacitive interaction between different double quantum dots, each occupied with a single electron. The benefit of this approach is that it's fast and all-electric. The downside, however, is that this type of qubit, a charged qubit, can decohere very quickly. The charged qubit can easily interact with other electric charges in the surrounding, and thereby lose its quantum mechanical state. Materials in a solid state have often traps or impurities, where individual charges can be trapped. And these traps are often unstable and will lead to fluctuations in the electric field. And this will lead to a displacement of the charge in the quantum dot and affect the energy scales. A change in energy will correspond to a change in the phase of the qubit, and thus result in qubit decoherence. Therefore, instead of using the charge, we often try to define qubits in a different way. Instead of the charge, we can make use of the quantum mechanical spin of an electron to define a physical qubit. In a magnetic field, the spin states are split in energy due to the Zeeman interaction. The spin states spin up and spin down define a physical qubit. Rotations from spin down to spin up can be made via microwave pulses. An AC magnetic field that is on resonance with the Zeeman energy will lead to Rabi rotations, and thus to single qubit operations. Two qubit operations can be achieved by quantum mechanically coupling different quantum dots. The resultant exchange interaction alters the resonance energies, such that qubit operations can be performed that depend on the state of the other qubit. Native two-qubit gates for quantum dots include the swap, the C-ROT, and the C-phase operation. Later in this lecture, we will explain how these operations function. The benefit of using the spin degree of freedom to define the physical qubit is that the qubit lifetime, the so-called T1 time, can be very long and significantly beyond a second. Also, the quantum coherence, the phase coherence of the qubit, can be very long, the so-called T2 time, and can reach up to tens of milliseconds. Before going to more detail in explaining how these operations work, let's look at even further options to create qubits with quantum dots. In the last 2 decades, several types of quantum dot qubits have been proposed and have been experimentally realized. Next to the single electron in a single quantum dot, which is also called the Loss DiVincenzo qubit, named after its inventors, there are several qubits based on multiple electrons and/or multiple quantum dots. Singlet triplet qubits are based on 2 electrons residing in 2 quantum dots. In the presence of an exchange interaction due to the tunnel coupling, a qubit can be defined on singlet and triplet basis states. Such a qubit may be more resilient against magnetic field noise, and, depending on its implementation, may allow for all-electric control. Singlet triplet qubits have been experimentally demonstrated, and even 2 singlet triplet qubits have been entangled together. Even more exotic implementations are the quantum dot hybrid qubit and the exchange-only qubit, and alternative versions thereof. These qubits are typically fast and can be controlled all electrically. Currently, the state-of-the-art is defined by Loss DiVincenzo qubits, and in particular, 4-qubit logic has already been demonstrated in a 2x2 two-dimensional array by defining Loss DiVincenzo qubits using holes in planar germanium.